Hi everyone, I'm Moin Ghaniyun, and in this recorded talk, I'm going to present our recent work on developing a PreSilicon framework for discovery and analysis of transient execution vulnerabilities. First, I'm going to cover some introductory notes on speculative execution. So speculative execution has become a must-have feature for almost all mid to high range processors. But just like many other performance optimizations that introduce security vulnerabilities, speculative execution is not an exception here. Recent works have demonstrated the existence of a vast attack surface on a speculative execution with the discovery of meltdown and Spectre attacks in 2018 that has led to an explosion of transient execution attacks afterwards. So since 2018, there has been many research papers targeting different transient execution vulnerabilities and exploiting various performance optimizations that all come under the umbrella term of the speculative execution. So attack papers like Cash Out, LVI, Fallout, Zombie Load, and Foreshadow are just a few prominent examples of the recent surge in the transient execution attacks. But just like the attack papers, there has also been significant efforts in both industry and academia to mitigate or detect transient execution vulnerabilities. So focusing on the verification tools, there has been a number of frameworks proposed like Transient Medusa, SpecFuzz, and SpeechMiner that are aimed for transient execution vulnerability detection. But the point is, discovering all paths that transient execution may lead to secret data leakage is not as straightforward. And this is simply because of the nature of the speculation, where the effects of the speculated instructions are rolled back after the processor detects misspeculation. So this actually creates a major roadblock to fully understanding the negative side effects of transient execution. To put it simply, the transient state will never be architecturally visible if the executed instructions are on the wrong path. So this actually makes the processor look like this closed box during the transient state where we don't have any information of what's happening inside this box. So that's why many existing tools used for transient execution vulnerability detection have to rely on covert channels or side channels to find the leakage and also guess the source of the leakage. But relying on these channels prevents a systematic evaluation of transient execution vulnerabilities as it limits the visibility into potential leakage to only known channels. So relying on these channels is very similar to guessing what's inside this box by just poking some holes on its surface and be content with the limited information that we get from these tiny holes. So in order to tackle this problem, our framework IntroSpectre integrates itself into the RTL verification flow of the design and gains full visibility into the internal state of the processor. This means that all relevant microarchitectural structures are monitored in a cycle-accurate RTL simulation. Now, going back to our box analogy, the box is open now. We can see what's inside. We don't have to rely on any channels. We don't have to poke holes. We can clearly see the information inside this box, which means that we can conduct a systematic evaluation of the design. So for the outline of this presentation, first, I briefly cover the big picture of IntroSpectre framework, then I'll dive into the design details, and finally, I'll share some evaluation results. So to get a better sense of IntroSpectre framework, let's assume that we have a black box instruction sequence generator here that generates some test code or assembly instructions that are responsible for priming memory locations or processor buffers with known secrets, and also directly or indirectly accessing these inaccessible secrets. Now let's assume that we take these test code and assembly instructions that we run them through an RTL simulator, where the RTL code of the processor is instrumented to include all microarchitectural structures state in every simulation cycle. So this RTL simulator generates a very comprehensive and thorough simulation log that includes all microarchitectural structures state in all simulation cycles. And the last step, we analyze this log to see whether we can find a secret leakage in one of these structures. So now we want to see how this instruction sequence is generated. Here is where the instruction sequence generation stands in the big picture of our design. And we already saw that part of these instructions are responsible for accessing the inaccessible secrets. So how we can make sure that these accesses are done in a comprehensive manner, how we can make sure that we exhaust all access strategies and depending on different microarchitectural state of the processor. To this end, our framework uses a set of targeted gadgets and employs a guided fuzzing approach to select relevant combinations of these gadgets and combines them together to generate test cases that are run through the RTL simulator. And the final output of the fuzzer includes instructions for both priming and also accessing the secret data. Here in this figure, you can see a simplified version of our fuzzing framework, where at the left, we have the pool of different types of gadgets that are fed into the fuzzer, and the fuzzer selects and combines different gadgets together to form the final test code. So instead of just randomly combining some random instructions, our fuzzing framework leverages from gadgets as its building blocks. So we have three types of gadgets. And the first is main gadgets, where these gadgets are the core of the leakage test sequence. They include the speculation primitives and also access instructions. We also have helper and setup gadgets, where they help the fuzzer to groom their microarchitectural estate for the proper execution of main gadgets. I should also stress that we don't limit the fuzzing to only combining these gadgets. Actually, most of our gadgets are parameterized. So this means that these gadgets come with some parameters that are randomized during the instruction generation, that they finally add another dimension to the fuzzing space. So starting from main gadgets, many of these gadgets are crafted based on known transient execution attacks, and the rest target corner cases by executing exception-causing instructions and also employing tortuous instructions like back-to-back loads, back-to-back store, store-to-load forwarding, or any other interesting combination of instructions that may put the processor in a state that we may see on deterministic behavior. Important point about these main gadgets is that main gadgets can benefit from certain microarchitectural states. So this means that it's more likely for these gadgets to show their intended behavior if a certain microarchitectural state is ready for them. So as an example for this, we have meltdown US main gadget here, which is a simple load instruction from supervisor address to register X10. So the requirements for this gadget is that the supervisor address should be present in L1D cache. So this means that if we prime the L1D cache with the supervisor address, it's more likely for this gadget to show its intended behavior and to be properly executed. But how we can fulfill the required microarchitectural state for main gadgets? So in our fuzzing framework, we use helper and setup gadgets to do that. These gadgets are selected by fuzzer based on the requirements of main gadgets. And the only difference between helper and setup gadgets is their execution privilege. So setup gadgets are executed in higher privileges like machine mode, supervisor mode, and helper gadgets are executed in user mode. So here at the right side of the slide, you can see that we have some examples of these gadgets. So for example, we have bring to data cache, which primes the data cache with the required address. We also have bring to instruction cache. We have bring to LFB, different levels of delay. So all these gadgets help the fuzzer to groom the microarchitectural state of the processor for the proper execution of main gadgets. To generate more meaningful test sequences, or basically to make our fuzzer smarter, our framework constructs an execution model along with the instruction generation. That this execution model acts as the core of our guided fuzzing approach, which helps with the gadget selection to generate more meaningful and more useful instruction sequences. The execution model actually predicts the behavior of the fuzz code by estimating the microarchitectural effects of adding each instruction to the fuzzer's output. So we all know that the execution of each instruction affects the state of the processor in some way. The execution model is there to capture these effects. So in summary, the execution model assists gadget selection, instruction generation, and also leakage analysis. But I covered the last one in the upcoming slides. So here we go through one full cycle of the instruction sequence generation. The first step is that the fuzzer randomly chooses one of these main gadgets from the pool of main gadgets. And as I already mentioned, these gadgets come with requirements for better execution. So in the next step, the fuzzer checks the execution model to see whether these requirements is fulfilled by the execution of previous instructions or not. And in this case, the microarchitecture is not ready, which means that the requirements are not fulfilled. And in the next step, the fuzzer carefully chooses from helper and setup gadgets to fulfill these requirements. And in the next step, the execution model gets updated based on the selected gadgets to reflect the effects of the selected gadgets. And finally, we have the fuzzer output constructed based on the gadgets chosen by the fuzzer. So far, we have covered that the instructions are generated by our gadget fuzzer, and then they are executed on the RTL simulator, which generates a very thorough simulation log. Now it's time to analyze this log to see whether we can find the secret leakage in any of these structures or not. So now let's assume that here is the part of the simulation log generated by the RTL simulator. The first step to find the secret is that a detailed secret timeline is automatically drawn using the execution model snapshots that are taken after adding each instruction to the fuzzer's output. So whenever the fuzzer decides to add an instruction to its output, it takes a snapshot of the state of the execution model at that point, and it stores these snapshots that are useful for the analyzing phase. So based on these snapshots, a secret timeline is drawn that specifies what values should be considered secret during different stages of the program execution. So whether a value is a secret or not depends on the execution privilege of the processor at that point, and also the permission bits of the memory page holding that value. So for example, for the execution cycles between Tm to Tn, this means that the execution cycles after cycle number m and before cycle number n, we have value 1, but this value is not secret. So this means that either the processor has the right execution privilege to access this value, or the permission bits of the memory page holding this value are accessible. So for Tn to Tp, we have 2 values, but none of them are secrets again. For Tp to Tq, value 1 is secret now. So this means that either the processor has lost its privileges to access this value, or the permission bits of the memory page holding this value has been changed, and this value is inaccessible. So for TQ to TR, both values are secret, and for after TR, value 1 is not secret anymore, but value 2 is still secret. So now let's assume that our analyzer finds value 2 in LFP entries for the execution cycles between TQ and TR. So now let's say that we find this value 2 among the LFP entries after execution cycles in TQ and TR. So this means that we have found a secret leakage, because this value is should be considered secret between the execution cycles TQ and TR. So let's move on to the evaluation. We evaluated IntroSpectre on RISC-V BOOM processor version 223, a single core configuration, using the very later RTL simulator version 4. And out of around 100 fuzzing rounds, we've been able to discover 13 distinct scenarios leading to secret leakage through different microarchitectural structures. And many of these secret leakage scenarios haven't been reported before on BOOM processor. We categorize these leakage scenarios across 3 classes. And the first type is the R-type leakage, where we found the secret data in both register file and LFP. The second type is the L-type leakage, where we found the secret data only in LFP. And the third class is miscellaneous. It's control flow related leakage scenarios, where we have 2 instances of Meltdown JP and Meltdown X. So here is the full list of our leakage scenarios found in BOOM version 223. The first type, R-type leakage scenarios, you can see that in the BOOM core pipeline, they were leaked from physical register file and line field buffer. For the L-type, we found the secrets only in the line field buffer, and for miscellaneous, the leakage was related to the reorder buffer and also L1 instruction cache. So starting from the top, the first leakage scenario is supervisor-only bypass, where we bypass the supervisor-only memory. It's very similar to the first variant of Meltdown. In R2, we bypass the user-only memory. And in R3, we bypass the machine-only memory, which is actually bypassing the security guarantees of RISC-V physical memory protection. So I'll dive into the details of this leakage case study of machine-only bypass. So RISC-V physical memory protection is the backbone of many trusted execution environments developed for RISC-V ecosystem. And in this leakage scenario, we're going to show how we bypass the security monitor memory isolation in Keystone framework. And Keystone framework is one of these trusted execution environment frameworks developed for RISC-V systems. So here is the memory structure of a Keystone enabled system. So the Keystone divides the memory into 2 segments. And the first segment is the security monitor itself, where this security monitor is inaccessible to a supervisor or a user execution privilege. It's only accessible to machine mode by the code inside this security monitor region. And the security monitor is protected by physical memory protection. So this means that we cannot access the security monitor without machine mode privileges. And the security monitor is responsible for creating, running, and destroying secure enclaves. So here are the gadgets selected by our fuzzer for this fuzzing round, that these gadgets were run through the RTL simulator, and in the simulation log generated after this fuzzing round, we've been able to find security monitor secrets in both LFP entries and also the physical register file. So in this leakage case study, we've been able to bypass the physical memory protection guarantees of RISC-V system in BOOM processor. And we've been able to leak secrets from the security monitor memory in Keystone framework. So in the first three R-type leakage scenarios, we bypassed all 3 privilege levels of RISC-V specification. In the next 5 R-type leakage scenarios, we read from inaccessible user pages. So in the first one, we read from invalid user pages. We read from user pages without read permission, read from user pages with both access and dirty bits off, with access bit off, and with dirty bit off. So these can be categorized as leaking secrets from inaccessible user pages. The next class is L-type leakage, where in the first instance, we leak page table entries through LFP, and we leak secrets of a page without proper permission in LFP by using the effects of the prefetcher. So this means that the prefetcher does not make any permissions check when accessing the memory region. And for L3, we leak supervisor secrets after handling an exception through LFP. So all these 3 can be categorized as potential secret leakage from LFP, as they couldn't make the secrets couldn't make their way into the register file. And the last class of leakage scenarios is control flow related, where in the X1 we jump to a memory location and execute the state value, and the processor does not raise any exceptions, and the control flow of the program completely changes, and this is clearly a bug. In X2, we speculatively execute supervisor code or inaccessible user code while we are still in user mode execution privileges. So these 2 can be categorized as illegal speculative control flow. We examined the coverage of IntroSpectre along 4 dimensions. And the first dimension is the coverage of microarchitectural structures, where all relevant microarchitectural structures state are monitored in the simulation log. And the next dimension can be the isolation boundaries, where all possible accesses across all isolation boundaries are covered in our framework. And the next dimension can be the coverage of gadgets, where we have all known and applicable meltdown-like attacks were covered in our gadgets, and we also have some other torturing gadgets for the to increase the fuzzing entropy. And finally, regarding the false positives and false negatives, and we don't have any false negatives regarding the leakage scenarios that are triggered by our fuzzer, but we cannot guarantee that we capture the leakage scenarios that are not exercised by our test code. And regarding the false positives, if the IntroSpectre alarms that we have a secret leakage, this means that we are 100% sure that an isolation boundary is bypassed, but we might have false positives regarding the exploitability of that secret leakage. This means that we don't know if we have the channels to leak that secret, basically. So in summary, we developed IntroSpectre as a framework for transient execution vulnerability detection. We gain full visibility into internal state of the processor, and this enables us to conduct a systematic evaluation of the design regarding transient execution vulnerabilities. And in this work, we focus on meltdown-like attacks, but this tool can be extended to cover other transient execution attacks like Spectre attacks. The source code of IntroSpectre will be available soon at my GitHub page, and you can email me or message me anytime in Twitter regarding questions about the paper. Thank you.